from Tsinghua University. First of all, let me thank the organizers for inviting me here to this very exciting workshop. Today I'm going to talk about Cuprate superconductors from the point of view of pure condensed matter theories. Since this problem has been studied like 27 years, a lot of proposals and have been made, and so I think the best way for me to present here is to try to give you a coherent story based on my own perspective, so that for many of you in the string theory community who are not familiar with the ITC cuprates could get a sense of some key issues and challenges we are facing. So here's the outline of my talk. I will first briefly make the introduction of some basic experimental phenomenology of ITC cuprates. Then I will point out that cuprates as doped Mott insulators. In other words, the interaction is very important, which are widely accepted by the community. And after that, I will talk about some basic properties of Mott physics. Especially, I will point out the important sign structure, which derive from fermion signs, but because of interaction, which will make a dramatic change of the sign structure, which will play a critical role to the Mott physics. I will give you several examples. I will focus on the one-hole case where we have a numerical calculation shows how this sign structure plays out, which gives you long-form liquid behavior. And then I will give you some pedagogical picture about finite doping and the global phase diagram. If at the end I still have time, I will talk about ground state wave function briefly. In 1986, these two gentlemen discovered that the cuprates actually has exhibit high TC superconductivity, over 30, and within a very short time, few years, the TC has been raised up to actually it's more than 140. Under pressure, its highest record is about 164, and it stays there. But this record, you see all these red dots, which really stick out compared to all the other superconductors, including recently discovered iron nictide superconductors, where highest TC is 55 Kelvin. So the big question here is whether these new superconductors, cuprate superconductors, are still described like BCS superconductors, or they are some new state of matter. And the related question would be that for conventional superconductor, BCS superconductor, when the temperature reaches beyond critical temperature, you will get a so-called Landau Fermi liquid state. But the cuprates will have a quite dramatically different behavior above superconducting transition temperature, especially the low doping. And for the Fermi liquid case, basically electrons fill up the Fermi sea, and the low-lying excitations happen around the Fermi surface, which will contribute some typical Fermi liquid behaviors. For example, specific heat will have a linear temperature dependence, and the Pauli spin susceptibility has constant behavior, or the nuclear magnetic resonance shows so-called the relaxation rate shows a linear T behaviors. All these behavior actually persist when you turn on weak interaction, which will change, renormalize the excitation around the Fermi surface, and make this momentum jump from 1 to some reduced value, which is the quasi-particle weight. But for the high TC cuprates, this is the Sommerfeld constant. This red dash lines the Fermi liquid behavior, you see the above superconducting transition temperature, the gamma shows a strong temperature dependence, and this different doping concentration all deviate from this, clearly deviate from the linear, from this constant behavior. And this is a spin susceptibility, a different doping, and this is like a 1 T1 NMR relaxation rate. And let's focus on the say uniform spin susceptibility for 214 material. This is a different doping, and this is under doping, and all this data shows you cannot see any trace of polysusceptibility. In fact, you can this data can be rescaled into some kind of universal curve. This is slightly data massaged, but nonetheless you see if the peak value, the temperature scale with the peak value temperature, and the susceptibility divided by the maximum value. And this universal curve actually is not like a polysusceptibility contributed by the quasi-particle near Fermi surface. Instead, it's well described by this Heisenberg model where you have local spin which interact with each other through nearest neighbor super exchange J. But this J will decide this peak value. So you will have strong doping dependence. This effective coupling actually with a function of doping actually decreases monotonically. So this is a temperature. So below this temperature, above Tc, you see the suppression of uniform susceptibility, which people call the pseudo gap behavior, one of them. And in fact, in the past 2 decades, a lot of experimental have done all different kind of approach, transport, uniform susceptibility transport, NMR, photoemission, optical, Nernst effect, all other measurements show systematically that above the superconducting dome, you have some kind of pseudo gap behaviors. But notice that the temperature scale is quite different from different measurements. This is probably the highest one, and the Nernst is actually happens about up to 2 times of Tc, and at different temperature scale. Nonetheless, it tells us some universal behavior, all this cuprate material, which can be summarized as here axis is some kind of charge doping concentration, and their doping regime, you have a long-range antiferromagnetic ordering state, and the finite doping, you will have a high Tc superconducting state. But the interesting thing is that there's a huge range of in the phase diagram, you don't not necessarily have a true long-range order, but you see a lot of fluctuations. Actually, you can detect the antiferromagnetic fluctuation at order of J temperature. That's 1,000 Kelvin, and with decreased temperature at half filling or near half filling, you're going to long-range order state. But if the doping concentration is higher, you find that strong antiferromagnetic fluctuation actually will stop to develop long-range order at some low temperature. Instead, there's a strong antiferromagnetic fluctuation, superconducting fluctuation will come out. Eventually, it goes into the superconducting states. And this T0 we have seen in a uniform susceptibility. Actually, beyond this regime, you will see also very anomalous behavior, which is not like Fermi liquid at all. And there actually the strongest possible scattering to the electrons. And many people in this workshop will talk about the so-called non-Fermi liquid behavior in this regime. So only in the overdope regime, in a low temperature, there's an indication Fermi liquid possibly will get recovered. And there are actually many condensed matter systems. You have long-range antiferromagnetic ordering and superconducting state in the phase diagram. But there's a very important distinction is that in these like ionic tides, heavy fermion system, organic systems, looks like the normal state is not that different from Fermi liquid. So basically, it's the order competition between two different symmetry breaking state. But here, it looks like there's a a wide region of strong correlated fluctuating state, which behave like non-Fermi liquid. And especially the horizontal axis in other materials, you not only charge concentration, you can change like pressure, isovalent concentration. You get similar phase diagram. But here, the universal behavior only controlled by this x, this charge concentration. And in the Fermi liquid, the actual charge number is not that important. Important thing is the density of state in a Fermi surface. So you change Fermi a charge carrier, only you indirectly influence the probably density of states via the Fermi energy. But here, the cuprates, this all measurement shows that different properties sensitively depends on this x. This indicates that this system actually is a so-called dope Mott insulator. And so this picture was the first advocated by Phil Anderson actually right after discovering the high DC cuprates. According to his picture, and this one band, like large U Haber model, could describe this system where at half filling case, actually this system is become a insulator, but this is insulated is Mott insulator due to interaction, and therefore the x-axis you measure the charge doping into such a Mott insulator, and this x will really play an essential role here. And so to give you a very simple picture about Mott physics, take a band, okay, single band, and then turn on the on-site current interaction, and so this is a conductor band, and eventually, if you large enough comparable to the band width, then you have a split of band. And if Fermi energy at the second in the middle, that's half filling, then you find that this is an insulator, charge insulator. And I will take U even larger, and in this limit, you actually can use a local picture in real space where two electrons cannot occupy same side because of U energy. So at half filling, namely each side will with one electron, and you will reduce to localized spins, which described by Heisenberg model. And you see the no Haber band is filled up, such as each side there's one electron, but spin is not frozen yet, so could point up and down, and so there's only spin degrees freedom left. And if you dope this system, and by taking say electron out, then you have a hole here. The hole start to move, and it will carry charge, and that's the chemical potential move to a lower Haber band. And many people believe that to cuprates probably realistic case is for some intermediate U, like a flip. Some of them think this is quite important actually to understand cuprates. But here I will focus on this large unit, which give you a simplest picture, and we believe the physics is connect continuously.
So in all the pictures you've drawn of the Mott insulator, there's actually long-range antiferromagnetic order. And in fact, that state with the doped hole is the Fermi liquid. So what is that role going to play?
Oh, can you give a few minutes? I will come back to this issue a little bit later. Yeah, to address what you asking. So let me write down further the basic Hamiltonian large unit. The basic is so-called TJ Hamiltonian here, because the large U. So the double occupancy is forbidden here. So you have only single occupied electrons, or you have empty side. And then the two basic processes would be the super exchange process or the hopping of hole. And these two basic processes describe the simplest possible procedures in this system. And that half filling limit without holes, and this model reduced to Heisenberg model, which actually fits with experiment very well. So it's have been well established. The Heisenberg model actually described the cuprates at half filling, low line, low energy physics quite well. This is firm established, and so the challenge will be how you dope this system. Experimentally, you found that when you dope this system, okay, from that cartoon picture I just gave you, you would have some mobile charge, but experimentally shows that this charge, doped case, the charge will become metallic at high temperature, but in low temperature, there's resistivity divergence. In other words, this charge are also localized until some critical doping where it becomes superconducting, so the resistivity drop to 0. And in this regime, actually, you don't see very sharp quasi-particle peak. You see very broad features. So the question is, if you start from some well understood half fading, how you dope this system, first you probably experimentally shows that the charge are localized will coincide with long-range antiferromagnetic order phase. Then further doping will drive system into superconducting phase. At that point, antiferromagnetic long-range order is gone, but in the normal state, you will get in the underdoped regime, at least you have a pseudo-gap behaviors. So the question would be, if this charge localization is due to some Anderson localization because of impurity, or it's intrinsic. If it's intrinsic, then the charge delocalization, which leads to superconductivity, or is that given by destroying the long-range antiferromagnetic ordering? And if that's true, then the localization, delocalization, actual transition will be the underlying driving force for at least 0 temperature, underdoped cuprates. To answer these questions, let me come back to some very the standard understanding the condensed matter. That's a long interacting, weak interacting case, where we know there's a fermion sign, fermion system, non-interact. The wave function for identical particle will change sign under the switch of coordinate of identical particle. Then you have this for Fermi gas case, as I mentioned earlier. Turn-on interaction will reduce the quasi-particle weight, and if you formulate things in path integral, the imaginary time, space, and the partition function can be written in such a form where any switching of two identical particles will give you minus sign here, and NEX just keep track of the exchange between particles. Okay. And there are many attempts to try to show how you increase interaction to get rid of the Fermi liquid behavior. And one approach interesting is to follow the sign change of a wave function. There are the so-called polyhyperspace surface, and then you turn on interaction and approximate. Under some approximation, you can show that with increase of interaction, eventually this poly surface, you would have such a fractalized sign change regime, such that the Fermi energy will be driven to 0. This is an extreme limit where you can get long Fermi liquid behavior. But in the following, we're going to take a different route to look at this problem. And actually, in the conventional system, in nature, there's other ways to get rid of, to overcome the fermion sign frustration. It's by forming so-called off-diagonal long-range order or symmetry breaking. And for simplest symmetry breaking system, you can imagine that it's boson, with a symmetrical wave function, which will form a Bose condensation. But for fermion system, there's other way to manage to make bosonized. In the weak coupling case, the Coop pairing such that form a bosonic object when length scale is larger than the Coop pair size. Or in the case space, there's a thin layer of electrons near the Fermi surface will form a Coop pair. CDW, SDW, all kind of particle hole pair, so to form boson field, and such that you gain kinetic energy. But the problem of this all weak coupling case is that if your temperature is high enough to drive this order away, and the fermion sign, because there's a large Fermi sea there, so there's a normal state scale from liquid, just like Subir just pointed out. This all weak coupling case. You cannot get rid of fermion signs. But now let's imagine I have mentioned that if we increase the U large enough at half filling, we had another limit where this all spin are localized. This is described by Heisenberg model. In this case, if you write down partition function, what you see is that this all these paths actually become positive weight with this weight and without sign. The fermion sign is totally disappear here. So you see that in low temperature, this localized spin will demonstrate the long-range anti-fermi ordering, just like a STW case. But if you imagine to increase temperature to melt long-range order, then in the high temperature, you still see that this system different from Fermi liquid. By that, there's no fermion sign at all. So this is a simplest extreme case where it tells you the interaction will totally change the nature of the system by changing fermion signs. In fact, the fermions are still fermions, but if you switch two identical particles, they still change sign. But the issue here is that this process will not enter into real physical process because the Hilbert space is changed. You don't allow two double occupancy. So you cannot simply change these two particles in real physical process. The real physical allowed physical process is just to switch to this label anti-Fermi spins. So that's the essence of how the interaction changes the fermion signs, the half filling limit. Of course, it will be very interesting to see how this, when you increase the interaction, this fermion sign change from one limit to another limit. But for our purpose, I'm going to only focus on the strong coupling case and the doped system. That's relevant to the high TC cuprates, and we'll see what happens. Okay, now let's dope this system by taking one electron out. So suppose just consider one hole, then the hole can start to move because the spin can jump to this side. And then you find that the partition function will have some actual path associated with the hole's motion. And this path will have some sign come out. And this sign basically is the product plus minus sign, depends on whether hole exchange with up spin or down spin. So this sign just differentiated two different kind of polarization. So when hole complete the path, and you have this product of sign. This sign has nothing to do with fermion sign. It originates from there, but it's quite different. And this is something again to do with strong coupling. And then later on, it was found actually this sign structure holds for TJ mode for arbitrary doping, actually arbitrary dimension and temperature, as long as it's bipartite lattice. And this sign structure for the arbitrary doping actually those are two terms. One is H hole's motion associated with a string of sign we call phase string, and then there's additional sign. Now you have more than one hole. So there's a normal conventional statistical sign by switching two word line of two holes. And that's all you have. And then the weight here is always positive. So the sign rule would be like this.
What do you mean?
Yes?
The weight is a tau c in the weight, so that's not positive, right?
The weight here?
For these, so script z is positive, but the full partition function has the tau c.
Yeah. This is tau c is the sign structure.
Okay, but
yeah, so basically each path is
sum. You still have to do that sum over c, right?
Oh yeah, that's right. This is important, and that's the difficult part of this problem. But that means that every path there's a sign here, but you have sum up all the paths, right?
So for a fixed set of paths, this equation is positive in some.
Yeah.
But and also this break spin rotation invariance. I mean, can you do this in a spin rotation way?
Sure.
It does break spin rotation invariance.
No. They actually you mean spin rotation, right?
Sorry?
Spin rotation or other?
Just
this is
we break in spin rotation.
No, actually it just differentiates up and down spin. And actually, it doesn't matter whether you're up or down. And so you'll see this is just an exact formulation, so it doesn't depend on any.
If you do the exact sum and break, but any term seems to
Yeah.
practice you're
Right.
treating the two separately.
So I will show you below. We do numerical simulation. We don't involve any approximation to see how it plays out. Okay. So probably we'll come back to that a little bit later. So you'll see this sign is different from. Okay. Well, sorry. So sign rule would be that you have many holes here. The hole goes around closed path. You pick up a synchronous sign. Then you have two holes. If as identical particles, they switch each other. They can have minus sign coming here. That's all you have. And so this tells us actually this model. Actually, there's an emergent gauge force come out, and because of this synchronous sign, this one hole. And by analogy, in nature, you have all this weak, strong, or electromagnetic force, which all can be specified by long integrable phase factor for charged particle from going from A to B, a different path or different path. So this is exactly the same, except that this is on the discretized lattice. As this phase is actually Z2 plus or minus. Also, here it involves time, but here it's more like a burst phase. So it doesn't matter the charge move fast or slow, as it all counts how many spins exchange with the hole, like down spin exchange the hole. So it's more like a topological phase, and this kind of sign structure actually corresponds to a topological theory. It's called the mutual Chern-Simons gauge theory. Actually, I should mention that Subir and his collaborator had a mutual Chern-Simons theory for the not this large U, but the finite U Haber model. And recently, actually, we have been able to show that actually this kind of structure does persist into finite U. So you can connect smoothly from weak coupling U, where you recover full fermion sign, to strong U to Heisenberg model. And so we'll see. We'll be interested to see what's the detailed gauge theory, the mutual Chern-Simons gauge theory there. But today's talk, I'm going to focus on the strong coupling limit. And what we learned here is that the charged particle moving in the background, the vacuum actually full of spins, will pick up non-trivial synchronous signs. And this will create a tremendous problem for our perturbative approach to this problem. Because in conventional system, if the path is long enough compared to a lattice constant, and this path becomes very smooth, we can use semi-classical approximation, and the mean field theory would make sense. We can create a saddle point state and make perturbation. But this sign actually very singular, because one sign change will totally change the nature of each given path. And so you cannot do any approximation. And this could be regarded as the nature of this Mott physics. So Mott physics here shows that actually is that some kind of new sign structure replacing the fermion signs in non-interacting limit. And this strong correlation represents that charge here actually had a spin background, have a long range, entanglement. And this sign structure plus restricted Hilbert space tells us we have to really unique fractionalization to deal with this system. In other words, you have to make some duality, we call mutual duality transformation, in order to treat this system. You cannot use electron as an original basis to treat it. You would meet a tremendous singular perturbative problem. And so that's the moral we learn from this system. So if we imagine we have intelligent aliens live in the world of the Haber world, and their energy, they cannot get access to the Mott gap energy, and the accelerator energy is not large enough, then they cannot identify electrons in the system. They only can have some fractionized charge and the spins and then the gauge theory. And only when we look at the problem at the energy level, at the EV, then we can write down this Haber model or TGM model with electrons. That's because we can overcome the Haber U energy scale. So so at this point we haven't done any approximation, but as Spear mentioned, we have to sum up all kind of paths, and this is tremendously difficult unless we do some clever way to find some duality transformation. We can treat this system, but we have a numerical help to show how this science sequence can play out. And there's a very powerful method. It's called DMRG. It doesn't suffer the science problem. But the problem is it can treat one-dimension chain very well, or ladder system with stack of chains, but it cannot really go to two-dimension for larger system. But for us, actually, we don't need to go to two-dimension. As I mentioned, this science structure is proven for arbitrary dimension, and as long as it's a bipartite lattice. And so what we need is a very long line so that this interference of all different paths will play out. So we need a very long chain, but doesn't need a very large, numbers. And so this DMRG suits this purpose perfectly. And this is a calculation we have. And so for finite size, Nx is the size of this ladder, and the charge would localize, of course, bounded by this length scale of the ladder. And for one dimension, when ladder the chain's length increase, this width of charge increase linearly. That's, of course, is mobile, Latimer liquid behavior. But for 2-leg, 3-leg, 4-leg, 5-leg, something happens that when Nx large enough, it becomes saturated. In other words, it becomes localized, insensitive to the sample size. And this localization is actually very large. It's 50, 30. So it's much larger than what exact degradation can get access to. But still, it shows that very flat structure. And that's because different paths will have a strong destructive quantum interference, such as eventually hole will be localized in space. This is not Anderson localization. This is a translational system. This is really beautifully strong, quantum interference of this science structure. And if you turn off the interlayer, interchain hopping, then you don't have this interference, and you find that actually it slap back for the 2-leg case and the closed case. They become extended. And another probe is that you can actually switch off this size structure by putting sigma in this hopping term. And there's no size structure here, and you find that these 2-leg, 3-leg will slap back to the extended profile. And this model actually, sigma is just up and down, take the value of plus or minus, which precisely cancel out the size structure we see. And therefore, tau c is 1, and WC is the same as before. So we have two models. You can tune on this sign, turn off this sign, and do numerical simulation. And you find that once you turn off this sign, and the momentum distribution shows a very sharp delta peak at the K0. It tells you this doped hole really become mobile, become a Bohr state with reduced quasi-particle weight. And this is because only one hole, so it's not a Fermi, there's no state. It's just one particle here. But once you turn on the science structure in the TGA model, you see this distribution will have very strange behavior. The summation of it will give you one hole, because the sum rule gives you one hole, but you see this very rich feature. And there is a scaling law that notice that the nk is multiplied by n, so that this height actually proportional 1 over n. In other words, if there is a quasi-particle weight, will goes to 0. And this is a scaling behavior for 2, 3-leg, 4-leg, really tells you this is a localized profile.
This is the electron distribution function, the electron operator, NOK.
This is electron operator. You subtract the half filling. Half filling is flat. There's no Fermi.
What is the density of electrons?
I'm sorry?
What is the density of electrons?
Just one hole. This is the sum rule. This is momentum distribution. Sum up all of them, give you one. Let's just put one hole. So in other words, this hole will strongly interact with the background, and such that the momentum will be actually you spread out. This is localization feature. And as mentioned, this sign structure only works for bipartite lattice. If you add a next year's labor hopping, the sign structure will start to disorder. So you expect when T prime large enough, eventually the hole will become delocalized.
Does it depend on whether you get odd or even length?
Yeah, given D over J. For a given number, when you increase T prime.
The behavior in the vertical axis doesn't be different for 2 versus 3.
Oh, there's a 2, 3. We actually can get a 7. Yeah, there's a depends on
between odd and even.
Yeah, there's odd even effect. Yes, I didn't show the updated figure. Yeah, but we don't know about 7 above 7 what's a general trend. So this is basically this quasi one-dimensional system.
So, but if I take an even number of legs,
yeah,
and 0 doping,
yeah,
I believe that's a spin gap system.
Yeah,
Gaussian gap.
Yeah.
Confinement and everything.
Sure, we can get that.
So why do you think there's localization in that case?
Yeah, this is very important. When you have a gap, you normally think that the whole hopping will generate something with gap. So relation to this quasi-particle is weak, but because this sign actually is very cheap, turns out this non-perturb effect. Once you put one hole, everything is destroyed. So you don't have perturbative theory working even for 2-leg ladder. That's the moral of it.
What is an infinite ladder? How can one hole change the phase of an infinite ladder?
Yeah, but one hole is just change the hole's motion, right? So this is also one particle physics. The ground state is now changed.
What's the value of J in the previous?
Oh yeah.
No, in the previous figure.
I actually mentioned that all these calculations T over J equals 3. We checked over all values. And very small T, there's a phase separation or something. But generally, this will hold. Until T is like a 30 J, then you have some polarized polar come out.
Right.
That's like also polar.
So
I didn't have time.
Is there a way of evaluating starting with the infinite U case and enumerating the T over U corrections to this phase string?
Oh yeah, that's very hard. Actually, this U equal to infinity is a singular point.
It's a singular point.
Very singular
So
point.
what is to start from there and start systematically enumerating?
But still non-perturbative. That's the problem.
I don't know how you would do that, but I'm just wondering, have you?
Yeah, that's
You might do that.
I don't know. I don't know either.
Because that might be a way of understanding.
Yeah, I know what
you're getting
at.
this effect.
Okay. So, so the transition here, you just look at this is the first derivative of energy, the second derivative we repeat here, separate these two regimes, and these two sides, you see, again, you see a different scaling of momentum distribution for localized distribution for a very itinerant quasi-hole. And this is for ladder case. Now, how about 2-dimension? Analytically, you can imagine that because of the hole moved on the anti-Fermi background, you have plus minus sign because of the new order. But because it's quantum anti-Fermi, so there's a lot of 0-point motion. Such as the path, large enough path, you have sign mismatch. You can pick up all arbitrary plus or minus sign, such as the hole will not go back, will not have definite sign at this side, or create a destructive interference to make it localized. There's also other analytical way to discuss the localization at no doping, and some of from different angle to look at this problem. And so.
Sorry, I have real trouble with that result. So you have antiferromagnetic magnet with long range order.
Right.
And I mean, I thought the general belief was that if you put one hole, it is a quasi-particle finite residue with about a J over T. There's a lot of evidence to support that.
But the evidence is based on the small exact diagonalization. That's just too small.
Perturbation theory and high order spin wave expansion.
That's right.
Huge amount of work, large N expansion. They all support the idea that there is a well-defined quasi-particle when you have long-range antiferromagnetic order.
Yeah, but the same argument can be applied to the ladder case. As we showed in the ladder case numerically, you see this sign structure really non-perturbed to
I have trouble with the ladder conclusion too, but here it's a simpler case.
Yeah, so here is
order.
Okay, but I don't think that self-consistently you do see. You assume there's a quasi-particle weight. You do see.
all kinds of
but experimentally, you see photo emission, and all things tells you that quasi-particle weight is really broad.
Okay, I mean I agree. If you have finite density, all kinds of strange things can happen.
No. One hole. Up as this start from a half-field sample, they use a photon to knock one electron out, and that's one hole. This is a really broad feature. Okay, but the point I made here is just for ladder. That's for sure. This is just a generation for 2 dimensions, but that's not very essential here. And I want make it's essential actually. I want to still some time. I'll make some pedagogical description about what happened to finite doping of a hole. So the single hole in a magnetic background, the pickup lungs, this is a singular sign. We'll make it, localized, and then you can imagine you have a sufficient amount of holes, and the localization actually is not favorable to its kinetic energy. So you will try to become delocalized. The way to make it delocalized is that to somehow to make the spin paired in short range paired instead of long range paired. To avoid this long range phase fluctuation. And in this way, you find that the sign could be cancelled out. Presumably, the hole will become coherent, condensed. And this is like a delocalization, superconducting happening. So the Anderson's original picture of RVB actually is emergent here by doping the antiferromagnet into this RVB feature. And in other words, when we have localization, the delocalization transition to superconducting, actually antiferromagnet order will be driven into spin liquid with short range. And but there's a caveat here. We have to be careful. Actually, this doesn't necessarily tell you it's superconducting phase, because for such kind of spin paired state, short range paired spin liquid state, you can break up spin pair to create spin non-excitation. Once you have that in finite temperature, and the condensate hole will see that through this non-local sign, and the condensate will not be happy with that. So in the end, they will form current to screen this, to make this spin excite the spins paired up. So it's called spin rotan. And this is a way to ensure that superconductivity is stable over a finite temperature range. So in other words, you can make a superconducting decoherent or a phase transition by making this bond pair deconfined. So once you have free spin-ons here, and really it becomes a long superconducting state. So we have some kind of spin-on confinement, deconfinement transition coincide with superconducting transition. But this confinement is very weak. The cause the solid case is vortex antiferrous bonding. And so this would be the prediction for the excitation here. So let me, I don't have much time, so let me just give you some global picture what happened. This is a temperature doping and a very small doping. We know this state is really long-range antiferromagnetic order state, and then you dope hole, the hole will pick up some long trio sign, make it self-localized, and until some critical point where the ground state will be driven into a short-range order state. Once it becomes short-range ordered, the hole's phase disordering will be removed, such that it will become superconducting phase. But this superconducting phase is not simple spin liquid. Actually, the spin-on actually is modulated, linked with, locked with some vortex to form a spin rotan vortex in the superconducting state to make sure the phase coherence. So the transition was divided by the vortex confinement, deconfinement, and then you have a zero gap behavior there. And if you increase doping further, eventually this short-range RVB will be totally destroyed, such as you have a lot of free spin, localized spin there, the whole move on that bad. So you have a lot of entropy there in principle, and this hole will get strongly fluctuating. This is maximal possible fluctuation. This instead of localized hole actually make a diffusive behavior. That's a strange metal behavior. But this state actually in the zero temperature is not stable because the huge fluctuation on kinetic energy. So it turns out the spin and the hole would like to bond together, such as each type of hopping, the hole will exchange with this backflow spin, such as this size structure become trivial, become all same sign. And therefore, they will recover fermion, this quasi-particle with same quantum number, and the two of these objects just satisfy fermion statistics. So this is roughly what happened here. And there's a actually it's a simple wave function can describe it. And this wave function, the most important thing is in fact you have this simple Joster type factor which keep track of this sign structure. So it's no longer fermion sign. So this is something new sign. And the rest of them just this anti-fermion background, which turn to short range anti-fermion. Then you, by putting holes there, by taking electron out in pairs there, and then you have some kind of version parameter which can be smoothly described in this new formulation. And I think let me just go to the conclusion. My time's up. So in this talk, I tried to I have shown some key basic experiment phenomena for the cuprates, and I point out that many people believe that this is a doped model insulator with a strong interaction. And I have pointed out actually the Mott physics is a simplified model that harbor a TGA. There's an altered sign structure from the fermion signs by interaction, and that causes a huge difference compared to firm liquid, which is the basis for fermion signs, constitute the basis for the firm liquid. And I didn't have much time to talk about the ground state wave function, but I think I will stop here. Sorry for the overtime. Thank you.
Let's take one question.
I have a question, but maybe somebody else.
I have a question. Somebody else.
Different question.
Yeah, you mentioned that the Chern-Simons gauge theory emerges from the large U model.
Yeah.
What's the gauge group?
Okay. Basically, it's U1 cos U1.
U1
Cos
plus
U1.
U1.
Yeah.
I see.
Yeah. So you have a two. Now you have a two kind of different matters field: charge holon and these neutral spin-on, and they talk to each other through this.
The Chern-Simons terms come in with opposite sign. In holography, we have a well-known gauge theory that has this feature.
So basically, what you see is up and down. We are having different the flux tube. The charge will talk to them. And that's so that doesn't break time reversal because up and down will have different sign.
Interesting.
Okay.
Well, I mean, so you're obviously implying that there's some normal state in the pseudo gap or strained metal that's a non-Fermi liquid.
Yeah.
Can you summarize what is the characteristics of this non-Fermi liquid? What are its quasi-particles? Is there a Lagrangian theorem?
Oh yeah, there are a lot of things, but
Well, in 1 or 2 seconds.
so
let's
okay,
take
the summarize. That's very good. Okay. Anyway, so basically, what happens in this system? Also, it's a sign structure very singular. The electrons fractionized. So in normal state, basically, it's all fractionized. So that's the reason cause all this alpha behavior. But only in the ordered phase, it start to recover the quasi-particle become coherent, everything. But in the normal state, the quasi-particle all incoherent. We can discuss this.
Okay.
Should this be
No, that's good.
over the full screen?
Okay, so